and welcome to section 9.3 video lecture, putting it together, which procedure do I use, the last video lecture of this chapter. So the goal of this lecture video is not really, in this section, is not really to teach you anything new, but just help you learn how to pick the right method. Because so far we've kind of split them into groups based on whether what we are looking at. So first thing first, this part of the flowchart at the bottom we can get rid of. That's from an older textbook. We don't really care whether sigma is known or unknown, because almost never will you know the population standard deviation and not know the population mean. So there's really only two options. First, is it a proportion? And in that case, you're checking this out. Is n times p hat times 1 minus p hat greater than or equal to 10? If that works, then you can do a 1 prop z int using your calculator. If you're using a mean and n is greater than or equal to 30, then you can compute the t interval. And if it's not, you need to find out if the data comes from a population that's approximately normal with no outliers. If the answer to that is yes, then you can compute the t interval. And if the answer to that is no, you need to do what is called a normal probability plot, which we'll talk about how to do here in a moment. So what I want to do to start out is we're just going to run through these first three problems together fairly quickly. They should be similar to problems you've seen in section 9.1 and 9.2. And then after we've done that, I'm going to ask you guys to pause the video and try these last 6 problems on your own, and then we'll go through them. Okay, so here we go. So in a survey of 1,800 adult Americans conducted April 2nd through the 5th, 2007, the Gallup organization asked, are you worried or not worried about having enough money for retirement? Of the 1,008 surveyed, 567 stated that they are worried about having enough money for retirement. Conduct a 90% confidence interval for the proportion of adult Americans who are worried or about having enough money for retirement. Okay, so the key here is which one of these are we doing, a proportion or a mean? And we can tell we're doing a proportion because it tells us that, right? They want to look for the proportion. So to check and see if we can find a confidence interval for this, what we want to do first is take n times p hat times 1 minus p hat. So n in this case is 1,080 and x is 1,008. X is 567, and so p hat is 567 divided by 1,008. So to do n times p hat times, so we do n times p hat times 1 minus p hat, and we see if that is greater than or equal to 10. So that's 1,008 times 567 over 1,008 times 1 minus 567 over 1,008, and we want to know is that greater than or equal to 10. And then if we want, we can do a little simplifying before we put this in the calculator. These cancel, because 1,000 divided by 8, 1,008 divided by 1,008 is 1. And so we can plug the rest into our calculator. So it's in the scientific part of our calculator, we're going to do 567 times 1 minus 567 divided by 1,008. And we do that, we get 248. So 248 is greater than or equal to 10. So that means we can do a 1 prop z int, and we can just do that using our graphing calculator. So we go into our class calc app, we change over to the graphing calculator, and we choose stat tests 1 prop z int, which is over on the left hand side there. And so then it asks us for x, n, and the c level. Okay, so what we're doing is 1 prop z interval int, and we want to put in x, which is 567, n, which is 1,008, and the confidence level, which is 90%, so 0.9. Okay, so that's what's going to go in our calculator. So we've got 1 prop z interval, we put in 567. 1,008 and 0.9. And so we get the interval 0.537 to 0.588. So somewhere between about 54% and 59% of Americans are worried that they won't have enough money for retirement. Okay, so that's the idea. So there's one with a proportion. So now let's flip over to the next page. Now, these are both going to be means, right? And if we knew what the mean was ahead of time, we could use the calculator to find these like we did in section 9.2. But because we have the data set, we want to use StatCrunch is going to be the best way to do this. So it says a police officer hides behind a billboard to catch speeders. The following data represent the number of minutes he waits before first observing a car that is exceeding the speed limit by more than 10 miles per hour on 10 randomly selected days. Construct a 95% confidence interval if possible. So the first thing to notice here is n equals 10, which is not greater than or equal to 30. So that means we cannot assume that this thing is normal. Also, in the problem, they don't tell us anywhere that this is normal. So how do we check and see if it's normal? Well, we can do that in class calc. So if you have your data in class calc, so like I said in the section 9.2 video, I've got all of my data here from all of the problems in chapter 9 notes. So the first thing we want to do is we want to make sure that this thing is approximately normal so that we can use the t-test stuff we're doing. So the one we want to pick in here is the QQ plot. So that's not what I called it before. I called it a normal probability plot. That's what it's called in our textbook. But in StatCrunch, it's called a QQ plot. So to do a normal probability plot, in StatCrunch, you're going to go, let's just go through those steps again. I already hit it once, but you're going to go to graph and then QQ plot. Okay. Graph and then QQ plot. Okay. And then we're going to pick the data we want to look at. So in this case, it's the minutes for speeders. And then what we care about is normal quantiles on the y-axis. Okay, so that's the one we're looking at. So we're looking for the normal quantile on the y-axis. That's the normal probability plot. Okay, and then I hit compute. And what I'm looking for is I'm looking for this data to be approximately linear. So see how it's got this red line that it added, and then we can see all the points plotted. And what we see is that it's not. Okay, so what we can say is we can't do a t-interval here. So when we graph this, the plot is not approximately linear. So the data is not approximately normal. So we cannot construct a t-interval. And that's the end of the problem. That's all we can try and do. Okay, so in the next one, the same type of thing happens. So we've got n is equal to 12. That is not greater than or equal to 30 again. It doesn't tell us that this is normally distributed. So we have to do a QQ plot again. We have to do a normal probability plot. So I'll go to my data, close out the one I just did. We're looking at the M&M column this time. So I go graph, QQ plot, choose the M&M column, and then don't worry about the group by. Sorry, I clicked on that. And then click normal quantiles on the y-axis and hit compute. And in this case, you can see that that is pretty close to linear. Those fall very close to the line. So you could say the normal probability plot is approximately linear. So we can construct a t-interval. Okay, so now we do what we did in section 9.2. In StatCrunch, we can close this out. We're going to go stat, Mine's already open because I was doing this video earlier today. So stat, I'm going to click T-stats. Then I'm going to choose with data because I one sample and then with data. We pick the column we're looking at, which is M&Ms here. I choose confidence interval and I put my confidence level in, which is 95%. And I hit compute. And it tells me that the confidence interval is 0.853 to 0.868. 898, sorry. 0.853 to 0.898. So 0.853 to 0.898. So in this case, we can say the weight, the mean weight of all M&Ms is between 0.853 grams and 0.898 grams with 95% confidence. Okay, so that's the idea. So the only thing that's different here than what we did in section 9.1 and 9.2 is having to do this normal probability plot when our sample size is too small. So what I'd like you all to do is pause the video at this point, try the problems on this page 16 and page 17 on your own, and once you've done that, go ahead and hit play and we'll go through them together. Okay, so now that you've had a chance to try these on your own, let's go ahead and work on them together. So this first one says, in a random sample of 100 estate tax returns that was audited by the IRS, it was determined that the mean amount of additional tax owed was $3,421, and the standard deviation of additional amount owed was $2,503. Construct and interpret a 90% confidence interval for the mean additional amount of tax owed for estate taxes. So we can see here that we're talking about means, so that means we want to try and do a t-interval. And we can do a t-interval because n equals 100, right? We have 100 estate tax returns, which is greater than or equal to 30, so that works. So now we can do a t-interval. And in this case, we're going to want to use class calc because we're given the mean and standard deviation. So we come into class calc and we do similar things to what we did before for the one prob z interval. We go to stat, we go to tests, but this time we want the t-interval. Okay, right? Because the t-interval is the one with mean. We put in our mean, our standard deviation, our sample size, and our confidence level. So our mean is 3,421. Our standard deviation is 2,583. Our sample size was 100. And they would like us to do a 90% confidence interval. So 0.9 is our C level. And so that gives us a confidence interval of 2,992 to 3,850 dollars. So 2,992 to 3,850 dollars is where we would expect the population mean amount of tax additionally owed to fall. Okay, so that's the idea. So the next one says, in a February 2007 Harris poll, 881 of 1,013 randomly selected adults said that they always wear seatbelts. Construct and interpret a 98% confidence interval for the proportion of adults who always wear their seatbelt. So notice in this case, it doesn't give us any means and standard deviations, and it asks us for a proportion. So we want to start by doing n times p hat times 1 minus p hat. So in this case, that's 1,013 times 881 over 1,013 times 1 minus 881 over 1,013. You can cancel those first two 1,013s, and so we we put in our calculator 881 times 1 minus 881 divided by 1,013. And so for that, we get 115, basically, if we round. So that's 115, which is a lot bigger than 10, so that works. So that means we can do a 1 prop z int. Okay, so go into class calc, go to our graph, go to stat, tests, 1 prop z int, and we put in 881 for x, 1013 for n, and 0.98 for our confidence level. And we get 0.845 to 0.894. Okay, so we found that in this by using this confidence interval, that about 84.5%, between 84.5% and 89.4% of the adult population in America in 2007 always wore their seatbelt. Okay, and then the last one says 50 rounds of a new type of ammunition were fired from a test weapon, and the muzzle velocity of the projectile was measured. The sample had a mean muzzle velocity of 863 and a standard deviation of 2.7. Construct and interpret a 99% confidence interval for the mean muzzle velocity. So in this case, right, we're looking at means. So we want to know, is the sample size greater than or equal to 30? Well, the sample size is 50. So that is greater than or equal to 30. So that means we can do a t interval. Okay. So then we can go to our calculator. And we can do stat, test, t interval. And we put in our x, which was 863. Our standard deviation, which is 2.7. Our sample size, which is 50. And our confidence level, which is 0.99. And we get 862 to 864. Okay. So we get 862 to 864. Okay, and notice in each one of these, I was kind of just choosing somewhere to round to. In the problems on the homework, it should tell you where to round to, so you won't have to worry about that. Just round to where it tells you to. And then on this last page here, we have 3 where we need to do the normal probability plots. So once again, I already put the data into StatCrunch. So if you were doing this on your own, you would have needed to put the data into StatCrunch. But anyway, so if we look at these. So let's just go ahead and start out, since we're doing these together, by seeing which ones of these we can do the normal probability plot with. Okay, so let's start by doing the graph of the QQ plot. And I don't know if it'll let me do more than one column at a time, but let's give that a try. So let's try doing all 3, the normal quartiles on the y-axis, and I hit compute. And there's the first one. So the first one is fairly linear, so we should be able to do a t-interval there. The second one is fairly linear, so we should be able to do a t-interval there. And this one is not linear, right? It's kind of like S-curved, so we can't do the last one. So if we go back to our notes here, we can say that this last one, is the normal probability plot was not approximately linear, and n equals 20, which is not greater than or equal to 30, so we cannot construct a t-interval, confidence interval. Okay, so that one we can't do, but we can go up to the top 2, and both of those were fine, so we can go ahead and do those confidence intervals. So bring up our data set. We had stat, t-stats, 1 sample with data, and let's try and do both of these at the same time. So I wanted to do gestation and stainmaster. I think that was supposed to be stairmaster. Based on the problem definition, but that's what I typed in. And they were both going to be 95%, so we can do these at the same time, I think. And I compute it, and it actually gives me both of them, right? So I get 262 to 273 and 101 to 117. So 262 to 273, and let me just check the other one real quick. 101 to 117. Okay, and that's it. That's the idea for how these work. So that's putting it all together. So This is the end of the section 9.3 video lecture and the chapter 9 notes. Make sure you're doing your homework on my math lab, and if you have any questions, feel free to email me, call me, or text me.